All right. So now we come to the part 3 of this course, which is on power semiconductor devices. So in our previous lectures, we have already studied some basic introduction of power electronics and its applications in multidisciplinary fields. In part 2, we have also studied some basic and important energy storage elements, which inductor and capacitance for configuration of important topologies for power converters. So we'll be talking about these topologies when we come to the chapter on power converters. And we have also studied that how to do power analysis, harmonic analysis for efficient calculation of efficiency in any power electronic systems. So now in this part, we'll be talking about the semiconductor devices, which are used as switches in power electronic systems. Okay, these power semiconductor devices used as switches in power electronics, they have two states. One is conducting, means when they are on, and the second state is off state, when they are blocking the current or non-conducting. And these switches, we can categorize these switches in three groups. Uncontrolled switches, an example is a power diode. So it has states, on and off states, controlled by the circuit itself. So we cannot control the on and off externally. The next one category is thyristor family. They are semi-controlled switches, means they are latched on by low power control signal, but must be turned off by power circuit. So it means we can control the turning on of these devices, these switches, but we cannot have an external control in our hand to turning off these switches. So they are semi-controlled. Turning on is controllable, turning off is not controllable. Now fully controllable switches, where we can control the turning on of these switches as well as turning off of the switches. So bipolar junction transistor, BJT, metal oxide semiconductor field effect transistor, MOSFET, insulated gate bipolar junction transistor, IGBT, gate turn-off thyristors, GTOs, and so on. These are some examples of controllable or fully controllable switches, where we can control the turning on or turning off both of these devices. And we'll be talking about all these categories one by one in this part of the semiconductor devices. So another definition, a unipolar device uses only one carrier type, either electron or holes, to conduct current through the device. A bipolar device uses both carrier types, electrons as well as holes, for current conduction. Okay, so now after these definitions, we can now start talking about the switch technology and how to classify these switches. So first one is uncontrolled switch. So power diode is a classical example of uncontrolled switch. And these power diodes normally are similar to the signal diodes, but the differences are that they can only be applied in power electronics or high power circuits. So how to differentiate these power diodes with signal diodes? That the current density over here is high. Because they are larger in area, these power diodes compared to the signal diodes are larger in area, thereby having higher current density, so the current rating can become higher. So they can sustain higher currents by increasing the size of the diodes, thereby increasing the current density. And for voltage rating, the depth of doped regions needs to be increased. So high level of doping as well as larger size will give us a high power diodes, where we have high current rating due to larger area, larger size, and high voltage rating due to the high level of doping. Okay, so now the working. A diode is turned on when it is in forward bias condition. Means when the anode is made more positive compared to the cathode. And diode is turned off, means in reverse bias condition, when the anode is made more negative compared to the cathode. So this is a symbol similar to the signal diode. The turn on and turn off of a diode, as we have said earlier, is uncontrollable. Means we cannot control either the turn on or the turn off. Only the circuit conditions will manage the switching on and switching off of the diode. Okay, now to talk about the IV characteristics, current voltage characteristics of the power diode, which is similar to the signal diode. The only thing is that the threshold voltage over here is much larger compared to the signal diode. So in signal diodes, we have about 0.6 to 0.7 volts of threshold in silicon diodes. In this case, the threshold voltage comes out to be about 2 to 3 volts, a much larger value. And then the current starts to flow in the diode, means the diode turns on after threshold, and the exponential growth of current happens. And the same is true for the reverse bias diode. As in signal diode, so the IV characteristics are similar. The only thing is that the voltage levels and current levels are different. And these are the characteristics for ideal diode, where the diode starts conducting not at the threshold voltage of 2 or 3 volts, but at 0 volts. The switch turns on instantaneously when it is energized or when it is forward biased. So no voltage drop is there when the diode is conducting. So it means power loss. In this case, it is conduction loss, because when the diode is in on condition, it is conducting. So during this conduction state, how much power is lost? That is called conduction loss. We'll talk about these losses later on in this part of the lecture. Okay, so this is the characteristics of ideal diode. This is the characteristics of a practical diode. Okay, after the current voltage characteristics of the diode, we should talk about the models of a diode. Physically, the diode characteristics, the IV characteristics, as we saw in the previous slide, look like this in figure 1. But when we use these diodes, we need to, in computer-based algorithms or computer-based designs, we need to model these diodes as close as possible to the actual diode, actual physical diode. So depending upon the applications, low-end or high-end applications, for low-end means approximation of a diode. So this is in figure 2 is the first type of approximation. One means this model in figure 2. It has some PN junction and connected to the source, the DC source in series. And the characteristics of this diode model in figure 2 looks like this, a straight line. A kind of a low-end model. A better model compared to this is in model 3, where this combination PN junction and the voltage DC voltage source is connected to resistance in series. And now this characteristics look like this, because now the resistance characteristics also come into play. And for even better model, we can use this branch like here, PN junction, DC source, and a resistance, internal resistance or internal source, which is equal to the threshold voltage over here. So these branches can be replicated in parallel. So in this case, in figure 4, we have 2 branches connected in parallel to each other, and we can have even a better characteristics compared to characteristics in figure 3. So if we keep on adding these branches in parallel, we can have a finer characteristics compared to the characteristics in 4, which can be as close as possible to the characteristics in figure 1. So this is how a static model of a diode can be developed depending upon the applications. For low-end applications, a low-cost model is possible. For high-end applications, a better model can be applied based on parallel combination of these branches depending upon how much finer we want this model. Okay. So now once we come to know that how to make a static model of this diode during the computer-based designs, so we also should know about the dynamics of these diodes. So when a PN junction is unbiased, means in equilibrium state, the doping provides free charge, same as in signal diodes. So near the junction, the charges cancel and we have a depletion region. So during this equilibrium state, a depletion region starts to develop. There we have a positive charge polarity over here and a negative polarity developed over here in the N region. And now this depletion region can behave like a capacitance. Okay, so now we apply the forward biased. And when we apply the forward biased, this depletion layer, the spacing becomes smaller compared to the uncharged or unbiased state. So when the depletion layer becomes smaller, we have a capacitance developed in between. Inside capacitance is known as diffusion capacitance during forward biased. Since we know that looking at the thin spacing of this depletion layer, the capacitance can have a large value. Now, when we go to the reverse biased, in reverse bias, now the depletion layer becomes wider. So now this depletion layer acts as a depletion capacitance. And the value of this depletion capacitance is lower compared to the diffusion capacitance as in the forward biased. So it means that during unbiased condition, a depletion layer starts to build up. When we go for a biasing, either forward or reverse biasing, the depletion layer keeps on changing itself. And the capacitance starts to develop. In forward bias, the capacitance developed is called diffusion capacitance, having a larger value. During reverse bias, the capacitance developed is called depletion capacitance, having a smaller value compared to the diffusion capacitance. So now these capacitances play an important part in turning off dynamics of the diode. So now we have come to know about what's the status of these depletion layers in unbiased condition, in forward biased condition, or reverse biased condition. Now the next step is how it behaves in a transition phase when we change forward bias to the reverse bias. So during that time interval, what behavior does it follow? What are the dynamics behind it during that shift from forward to reverse? Okay, so when we switch this forward bias to the reverse bias, the diode current starts to decrease and it reaches value 0 over here. So now the thing is, because of the charge carriers accumulated in the capacitances, unless the reverse recovery process is finished, we cannot start the new forward voltage or new switching on of the device. So it continues to conduct due to minority carriers. So until the complete diffusion capacitance is discharged, hear each other. And at this point, the recombination process completes. So now at here, the recombination process completes. So now we do not have any excess charge carriers inside the power diode or inside this device. So now this diode is now in steady state and it is ready to go for forward bias again. So this time period, starting from when the diode current reaches 0 before reverse recovery, till it is fully recovered with all recombinations of all these minority charge carriers, this time is called, time taken is called reverse recovery time. So if this reverse recovery time is changed, the speed of the diode will change. So for high speed applications, the reverse recovery should be very fast. So all the minority charge carriers in the opposite direction must recombine very fast, so that the reverse recovery time becomes shorter, and for the next cycle of forward biasing, the diode should be ready. Okay, so these are the dynamics of diodes. So once we know that, okay, based on these dynamics, how to classify these diodes, or how to select these diodes for our own applications. So these diodes can be line frequency or general purpose diodes, where the on-state voltage is very low, like 1 volt or even less, means the threshold voltage is very low. And the reverse recovery time can be very large. So if the reverse recovery time is large, so we have to wait for a longer time period before the next conduction starts to happen. So for low speed applications, we can use these diodes. But they can have a high current rating, these line frequency diodes, because they are slow in nature, have very small threshold voltage. They can have high current ratings, means larger current density. Very high voltage ratings means the doping levels can be increased. So more doping levels, we can have slower response. So more charge carriers need to be recovered or need to be recombined before steady state condition is achieved. So they are basically used in rectifiers, because in rectifiers we do not have high speed requirements, where we need about 50 to 60 hertz of frequency. And now the next type of power diodes is fast recovery diodes, where the important thing is reverse recovery time. must be very, very low. So they must be able to recover, they must be able to recombine their charge carriers within 1 microsecond or even faster. Power levels we can increase or we can decrease. And the basic thing is, for high speed applications or high frequency applications, these fast recovery diodes can be used. So power levels can be managed depending upon the size of the diode as well as the doping levels of the diode. And the third type is Schottky diodes, very low forward voltage drop, like similar to signal diodes, limited blocking voltage, so means not very high, about 50 volts or something. And now the thing is that small charge storage time. So they must be very fast. So the reverse recovery time should be smaller. Threshold voltage is also small. The blocking voltage, the forward blocking voltage is also small, as well as the reverse recovery time should also be very small, so that the faster response. So in that case, the applications can be switch mode power supplies, like in laptops or mobile phones and all this. So there we need faster response. So Schottky diodes can find applications in these applications, where the voltage levels required are not very high, and at the same time, the frequency of operation should be fast. So these are the categories of power diodes for different applications. Now, this uncontrolled power diodes, after this, we come to this semi-controllable switches. And thyristor family is a type of a semi-control switches. So in this part, we'll be talking about silicon controlled rectifier only. Because not all members of the thyristor family are semi-controlled switches. Like gate turn-off thyristor is a fully controlled switch. So, but still it is a part of a thyristor family. Means the structure, the internal structure resembles the thyristor family. Okay, but for semi-controlled devices, we will be talking about silicon controlled rectifier in thyristors family. So how it looks like. So this thyristor, this silicon controlled rectifier, it's a 4-layer device, PN, PN. So if we have 4-layer device, we have 3 junctions, J1, J2, and J3. And now this J1 and J3, if we connect this upper terminal, which is anode, and the lower terminal, which is cathode, if we connect this anode to the positive terminal of a battery and cathode to a negative terminal of a battery, then this junction 1 and junction 3 become forward biased. But junction 2 is reverse biased. So this is the actual structure of a thyristor, the SCR, and this is the 2-transistor model of a SCR. Before going into the working principle of or operating principle of SCR, we come to know that what are the methods of switching on of the thyristor of this SCR. So method A is the forward biasing of a SCR. So if we just use the forward biasing technique of SCR, this thyristor can be turned on. The second method is to turn on this thyristor through gate triggering. Means one is to connect this anode and cathode with a large value of a source or a battery or voltage to turn on this device. The second method is to connect a voltage source to the gate terminal, and we get a turn on of the device. These are the 2 methods. We'll be talking about these two methods in detail. Another method is the temperature-based method. We increase the temperature of the device and the charge carrier starts to flow, breaking all the junctions, and the thyristor starts to conduct. But this is a destructive way of triggering the or turning on the SCR. Another method is high dV by dt, rate of change of voltage. So high rate of change of voltage across anode and cathode. So this current is proportional to the rate of change of voltage. C is the capacitance developed inside the junctions. So high dV by dt is directly proportional to the current. So more current will flow and this SCR will start to conduct. But this high dV by dt is kind of a destructive approach to the turning on of the SCR, normally not used. So method A is also kind of a destructive method. It can damage the SCR. Means the gate terminal is not connected in this case. Only the anode to cathode voltage is applied. And in this case, J1 and J3, I will be talking about this in the next one. So this J1 and J3 and J3, they are forward biased and J2 is reverse biased. Method A first. So when these two are forward biased, J1 and J3 are forward biased, J2 is reverse biased. So if we increase this one, the anode to cathode voltage. So if we increase the anode to cathode voltage, J1 is already forward biased, J3 is also already forward biased. So if we keep on increasing the forward voltage over here, means anode is made more positive compared to cathode. So if we keep on increasing the forward bias voltage over here, now N and P, due to the reverse charge carriers, the breakdown will happen, just like the reverse breakdown in diode's case. So this PN junction is forward biased, J1. This PN junction is also forward biased, J3, because N is more negative compared to this positive. Now this N is more positive compared to P, which is more negative. And as we keep on increasing the anode to cathode voltage over here, at some point of voltage, avalanche breakdown occurs. And when the avalanche breakdown occurs, that voltage is called BF, forward breakdown voltage. So at this forward breakdown voltage, J2 also breakdowns. So J1 is forward bias, not blocking the current. J3 forward bias, not blocking the current. J2 now is gone through avalanche breakdown. Now it also does not stop the current. So heavy amount of current will flow in this device now with the larger value of anode to cathode voltage. So that voltage is now called forward breakdown voltage of a SCR, where the SCR now starts to conduct. But this method is destructive because avalanche breakdown occurs in this case, which can cause a damage, permanent damage to the device. So that's why method A is normally not used, where we need to do the breakdown, avalanche breakdown of a J2 junction. And now coming to the method B, gate triggering. So in this case, now the third terminal, gate terminal, is now connected. Anode and cathode, the device is still forward biased, but now the third terminal, gate, is also connected. This is called gate triggering, and this method B will be discussing in detail over here, because that's the main method normally used in all the SCR triggering applications. Okay, so a trigger signal is applied between gate and cathode. Between gate and cathode, a trigger signal is applied. So means at the base and emitter terminal of NPN device, just like a common emitter configuration of a NPN. So in this common emitter configuration, now this gate is made more positive compared to cathode. So when gate is made more positive compared to cathode in common emitter configuration, so now the transistor starts to conduct. And the collector current starts to flow over here. Because now this NPN transistor is conducting, this collector current starts to flow. So in that case, if this transistor NPN starts to conduct, this PNP voltage over here in the base, this base terminal also starts to flow the current, thereby turning on the PNP transistors. So due to the collector current flowing in this NPN transistor, which is conducting now, this base current is now flowing in the PNP and it starts to conduct the PNP transistor now. So now the collector of this PNP transistor, the upper one, so it is now connected to the positive terminal of this anode. So it is pulled high. So it is connected to the positive, a large positive value at the anode. So this process will now continue to flow because this collector current is flowing over here, which in turn keeps on energizing the base. Now, due to this base current, the collector current starts to flow, which in turn energizes this transistor. And now this current will follow this loop and it will never come out of the loop. So this collector turns on this device and this collector turns on this device, and this two transistor connection will keep on flowing the current in a loop forever. So if we remove this gate signal now, still this current will continue to flow in the loop. So if we remove this anode terminal now, then only the transistor will, the current in these transistors will stop. So as long as this anode and cathode are forward biased, this loop will continue to flow the current, no matter if the gate signal is removed now. So it means now this gate signal can be called as a trigger. So it only triggers for a small instant of time. It energizes this base, this NPN transistor starts to conduct. And once this transistor starts to conduct, this collector current will start to energize the PNP transistor over here. Now this transistor starts to conduct. This positive terminal of PNP is already there. Negative terminal of this common emitter is already there. So this transistor, this current in this loop will continue to flow no matter if the gate terminal is removed, if the gate signal is removed. So this current will flow as long as this anode and cathode are connected to the forward biased. So in this case, there is no avalanche breakdown. There is no damage, no destructive way of triggering the device. So that's why this method B, also known as gate triggering, is used in turning on the SCR. And for all the applications in this course, all the power converters in this course, we'll be using this method B, always, called as gate triggering. So in short, a small voltage between gate and cathode is applied, turning on this NPN transistor, which in turn will turn on the PNP transistor. And now these two transistors will continue to flow this current in loop as long as this anode and cathode are connected. So no longer it needs gate voltage over here. So graphically, these IV characteristics look like this. So method A is this one, forward blocking voltage. We keep on increasing the forward voltage until we reach this forward breakdown voltage, method A, the avalanche breakdown happens, and all of a sudden, the voltage, the switch closes, and the voltage across this switch, means across this SCR, drops. And the current starts to conduct the current. And the current shoots up. But it can permanently damage the device because avalanche breakdown happens over here. Because junction J2 is actually going through an avalanche breakdown. Now method B. Method B is this way, where the gate current, the gate pulse, the gate trigger is applied. Here the gate trigger was not applied, so that's why gate trigger is 0. So gate terminal was not connected. But if we connect this gate terminal, this before reaching the breakdown voltage over here, this device can be turned on much before this breakdown voltage when we apply the gate trigger. If we apply higher value of gate trigger, means larger current over here, the base current, this base current over here, this base current over here. If you apply larger value of gate current, because this is a base of NPN, but gate of the complete SCR. So this gate current is actually a base current of the NPN transistor. So if we apply higher value of gate current, so it can be triggered much earlier. So at a smaller voltage. So if we increase this this gate current, this NPN transistor will start to conduct at a very low voltage. So we keep on increasing the gate current, we keep on decreasing the forward voltage. And once, let's say now this gate current is applied over here, and now the breakdown happens over here. So, and not the avalanche breakdown, but at threshold, the junction 2 is forward biased, and due to this forward bias of junction 2, junction 1 is already forward biased, junction 3 is also forward biased, and if you apply this gate current, junction 2 also becomes forward biased. So no need of avalanche breakdown. So all these three junctions are now forward biased over here, and now the current starts to flow in the device. So it shoots up like this. And this value over here is called latching current, where the thyristor or where this SCR starts to conduct. So this is the holding current. So below the holding current, the thyristor will be turned off. So if we want to design a turn-off circuit of a SCR, we make sure that the during the turning off of the thyristor, the current should be below the value of holding current, so that the SCR becomes off. So okay, so this is the symbol of SCR, a P-N junction like diode, but a third terminal called gate is also connected to this symbol. Anode, cathode, and gate terminal. Now, if you're talking about the characteristics of this SCR, it follows the blocking voltage in forward direction, where the avalanche breakdown happens. And in the reverse bias also, it blocks the voltage just like a simple diode. So avalanche breakdown happens here also, and it can get damaged permanently. So it blocks the reverse voltage as well as the forward voltage. And in this case, this current flows only in one direction. So when the SCR turns off through gate triggering, the SCR turns on. So forward conduction, forward blocking, and reverse blocking. So for turn off, we need a commutation circuit to ensure the anode current falls below holding current. So that is called commutation. In AC circuits, normally we have positive half cycles and negative half cycles. So this, let's say this sinusoidal wave, every half cycle, it crosses the natural zero line of this voltage. So during that time, when it in AC circuits, it alternates between positive and negative half cycles. So when it crosses zero value, it automatically turns off the thyristor. So that is called forced commutation, natural commutation. It happens naturally. But in DC, we do not have alternate half cycles or alternate cycles. So in that case, we have to turn off this SCR forcefully. So we need to design a special circuit, an external circuit, which can cause the turning off of this SCR. So using this external circuit to turn off this SCR is called forced commutation. And this forced commutation we will be discussing in DC to AC inverter section. And natural commutation will study in AC to DC converters, rectifiers. So again, to remember, the idea is to ensure that the anode current in SCR falls below holding current so that the SCR turns off. And latching current ensures that the gate terminal, when the gate pulse is applied, the SCR reaches the level of latching current before it starts to conduct. So for turning on, the latching current is measured at the minimum value of anode current where the SCR starts to conduct. And holding current is the minimum value of that current, anode current, below which the SCR turns off. Now, other members of the thyristor family, gate turn off thyristor. So in this case, this is the gate pulse over here for triggering the SCR into on condition, into conduction. And this is the negative gate pulse to turn off the SCR. So here we don't need any external circuit for forced commutation. So a negative gate pulse can be applied to turn off the thyristor, which is gate turn off thyristor. So that's the only difference between, or that's the main difference between SCR and GTO. So this is the symbol that it can be turned on through gate and it can also be turned off through gate. So turn on through positive gate pulse and turn off through negative gate pulse. Another member of a thyristor family is bidirectional triode thyristors, also called triacs. So they are normally capable of conducting in both directions. So in that case, you can say, so the triac can conduct in forward conduction mode and reverse conduction mode. So 4 quadrants. They can have a forward blocking voltage and they also can sustain reverse blocking voltage. And they have a forward conduction mode and they are also turned on in reverse conduction mode. in both the directions the current can flow. They are bidirectional in nature. So the current can flow from MT2 to MT1, terminal 1, or MT1 to MT2. So a gate pulse is applied to turn on the thyristor. So they are just equivalent to two anti-parallel thyristors, SCRs connected. So if two SCRs are connected anti-parallel to each other, we can have a triac. Only due to this, we have a current conduction in both directions. So now coming to the controllable switches. So gate turn-off thyristor, GTO, a member of a thyristor family, it can conduct the current just like SCR, but we can control this turning on and turning off of the GTO. That's why it can be called as a controllable switch. We can control the on and off both. Like in SCR, we can only control the turning on. Turning off was not in our hand. So some external circuit is required. So the only difficulty over here is that during turning off, a large reverse gate current is required. So if we are using it for a very high voltage rating or high current rating, let's say 1000 to 2000 amperes or even 5000 amperes of current. So it needs about 20% of the anode current to turn off the device. So for 5000 amperes, 20% can be about 1000 amperes. So 1000 amperes of current is required to turn off this device, which is huge. Large power losses are incurred in this case and difficult to design the circuit. So that's the difficulty part over here. So that's why the gate drive circuit is difficult to design. And the ratings for this device are normally 5 kilovolt for voltage ratings and 5 kiloamperes current rating in the range of, so basically large values. So this is an example of a gate turn-off characteristics of GTO. So this gate drive circuit is connected to the gate terminal of this device, which can turn on and turn off of this, which can turn on the GTO as well as turn off the GTO using this gate drive circuit. But another circuit is added over here, which we will study later part of this lecture, a snubber circuit. So you need to remember at this moment that snubber circuit, we need to reduce the dV by dt, because dV by dt can cause false triggering of the, or false turning on of the SCR we saw earlier. Large dV by dt can turn on the SCR, which we don't want because it can be a destructive way of triggering it on. So that's why we need some circuit, a kind of a protection circuit, which can protect the device from large dV by dt. So this is that device, this is that circuit called snubber circuit, which is a simple RC circuit. In this case, it is RCD circuit, R, C, and D circuit. We'll talk about this. Okay, so now coming out of the thyristor family, come to the power transistors family. So these power transistor family is also a fully controllable device family. So we can control the turn on as well as turn off of the device. So, and in power electronics, as I said earlier, that these devices will not be running in linear region for power electronic applications. Only two states or two modes are actually used for power electronics. One is saturation region, where the transistor is called on, and a cutoff region, where it is called off. So basically two states only, on state and off state. And we all also know that these transistors, they do not have a latched mode. So the forward characteristics resemble the diode characteristics. No latching is required. At some threshold, they start to conduct. And these devices, in this family, power transistor family, we have these type of devices: bipolar junction transistors, metal oxide silicon field effect transistors, also called MOSFET, insulated gate bipolar transistors, also called IGBT. We'll be talking about these in abbreviations form. Gate turn-off thyristors, GTO. Okay, so the first member of this family, bipolar junction transistor, BJT. We already know the characteristics of these BJTs, the output characteristics over here in the common emitter configuration. And these are the ideal characteristics of this, that during turn on, the voltage drop in the transistor is 0 when it is on. And when it is off, the current in the transistor is 0. So if in on state, the voltage is 0, means power loss is 0 during on state. Conduction loss is 0. And during off state, we only have a voltage, so current is 0. So again, power loss is 0. So during off state, no leakage losses, nothing, so only 0 power loss. So in ideal switch, power loss is 0 whether it is conducting or not conducting, whether it's in saturation or in cutoff. But ideally, this is the characteristics in figure B. Okay, so the ratings for these devices are about 1000 volts or 400 amperes, less than the SCR, but still we can handle large amount of voltage and current using these BJTs, but far less than SCRs. And switching frequency is 5 kilohertz, a little bit more also possible. On-state voltage is 2 to 3 volts, means when the transistor is on, what amount of voltage is dropped across the transistor or across the switch. Because when it is on, it should be 0 ideally. The on-state voltage should be 0 ideally, but it is not 0, it is having some value. So if it is having some value, so on-state voltage means some current is already flowing. So if we have this value, so some power losses will be there. But in this case, it is on-state voltage, so it is a conduction loss. So the conduction loss will be there. Low current gain, the current gain is less. So we need high base current, and if high base current is there, we can have a high value of collector current, thereby increasing the, thereby we have a considerable amount of beta current gain. Expensive because of complex gate drives, because to design a gate drive circuit, it is complex. So that's why normally not used in power electronic circuits unless it is required. So how to improve the current gain over here? So we can use these BJTs into Darlington pair in the form of a Darlington pair. So if we configure these two transistors in Darlington, we can have a high current gain. So this is the output current IC, and this is the input current IB1. So the total current gain of this Darlington is IC divided by IB1. And IC we know is IC1 plus IC2. So we simplify to this one, which comes out to be IC1 by IB1 plus IC2 by IB1. IC1 by IB1 can be called as beta 1, means the current gain for transistor 1. And for transistor 2, we can multiply and divide by this part of the equation. Multiply and divide by IB2, we get beta 2. IC2 by IB2 is beta 2. So beta 2 is the current gain for transistor 2. And then simplifying it further, we get beta 1 plus beta 2 multiplied by 1 plus beta 1. So it means that deciding upon the selection of these transistors, individual transistors, high current gain transistors, and then connecting them in Darlington pair, we can have a larger value of current gain, which can overcome the disadvantage of this low current gain of BJTs in power electronics. So in power electronics, we can use this Darlington to increase the current gain. But still, the base drive circuit becomes more complex. So that's why it's not selected that often for application in power electronics. Now the next one is the MOSFET, metal oxide silicon field effect transistor. Again, ideal characteristics and the actual characteristics, IV characteristics. And their voltage rating is even lower, 500 volts, much lower than SCRs and even lower than the BJTs. Current rating is also lower. So they cannot be used for high voltage and current ratings or high power ratings in power electronic circuits. So for low power rating applications, it can be used. But now the main advantage is the high switching speed, sometimes going up to megahertz. So now, since they are fully controllable devices, the turning on and off is simple. For turning on the VGS, gate source, we can apply 15 volts or 5 volts depending upon our requirement, the application or voltage rating. So we just apply a gate signal over here with the circuit, with the voltage source connected VGS. And to turn off, we can remove this VGS and the gate terminal will be turned off. So adding 50 volts to this VGS, this MOSFET is turned on. Again, disconnecting this VGS means 0 volts, this device is turned off. So just by connecting and disconnecting this power supply or voltage source to the gate and source terminal, we can turn on and turn off the device. So we can control the turning on and turning off of the device, metal oxide semiconductor or silicon field effect transistor. Okay, now the thing is that the internal dynamics, the resistance, RDS, the dynamic resistance, the internal resistance between drain and source during the on state, means when the MOSFET is conducting. It actually limits the power capability of MOSFETs. So for high power ratings or high voltage ratings of applications, these internal dynamic resistance can play an important part in power losses. So that's why we cannot use these in high power rating applications, because huge losses can incur due to RDS, this dynamic resistance. Other way is to design this MOSFET in such a way that the RDS, means the dynamic resistance on resistance, is very low. So if we can design MOSFET having very low value of dynamic resistance during on state, we can save power loss. Now the next one is insulated gate bipolar transistor, IGBT. So IGBT is just a hybrid of BJT and MOSFET, a combination. So if we hybridize these two, the BJT, where the turn on and turn off is controlled by the base signal, the base current, and in MOSFET, the turn on and turn off is controlled by the gate voltage, VGS. And if we combine these two together, the gate behavior is kind of similar to MOSFET. So it means we can turn on and turn off this IGBT using gate source voltage And at the same time, losses are low as we have in BJT due to low onset collector emitter voltage. So both the advantages we can hybrid in IGBT, or we can combine in IGBT. Advantage of MOSFET, where we can easily control turn on and turn off with the gate terminal, and advantage of BJT, where we have low losses because the on-state voltage is very low. And in MOSFET, again, due to the internal dynamic resistance, the on-state losses can be higher. So the ratings of this IGBT, because if we combine BJT and MOSFET, the characteristics of them together, so the ratings can be increased. So in this, voltage rating can be above 3 volts or 4 volts or 5 volts. And current can be above 1000 amperes, much higher than the MOSFETs and BJTs. And the switching frequency can also become higher due to the characteristics of MOSFET. Now, another one, insulated gate commutated thyristor. So now it is a member of the thyristor family and operates just like a normal thyristor, but now the added benefit is that it can be turned off using gate seal, just like GTO. But the disadvantage in GTO was that it requires a complex gate circuitry or a high or large value of current to turn off the device. But in this case, this gate terminal can be used for switching on as well as switching off, just like GTO. But the benefit is that only a small value of voltage is required to turn off the device. We do not need a large signal to turn off this device, just like in GTO. So that's why this IGCT is kind of a latest technology, useful for power applications and high power applications, where gate circuitries can also be made less complex. And the added benefit is that this gate circuitry can be integrated on the same silicon because it is not that complex. So that's why this technology is kind of emerging, or you can say popular in power electronics field. And voltage ratings similar to the SCRs, and current rating also similar to the SCRs, frequency also similar, but the only thing is that it is fully controllable device, unlike SCR, and at the same time less complex gate drive circuit. And the on-state voltage is also very low, same as in BJT. So it carries more advantages compared to all other devices. And state-of-the-art switch. And this is a symbol of IGCT. Now switch comparison. So for very high power rating, SCRs are normally used for, and at very low frequency band. If we want to increase the frequency band or a frequency of operation, but then we need to lower down the power rating. GTOs and IGT, they fall in this category. If we want to go at a faster speed further, but we need to sacrifice on the power rating, then IGBT can be useful. Further going up the frequency speed or up the frequency of operation, but we need to sacrifice further in power rating, then we can use MOSFETs. Just like in smartphones. In smartphones, MOSFETs are used for power conversion, like DC to DC conversion and all this. Because here we need faster switching speed, and at the same time, we do not need high power rating. Laptops, smartphones and all these applications, MOSFETs are used because power ratings are not high, but switching speed needs to be high. So this is how the comparison graphically we can see. If we compare the switching speed and power capability in tabular form, we can say, so BJT can handle medium power as well as medium switching speed. Like in this case over here BJT will come into picture. But normally they are not used because of all the disadvantages we have discussed earlier. That's why in power electronics, BJTs normally are not used. That's why I have not put it over here. But just for comparison's sake, MOSFETs handling power capability, then they can handle very low power capability, but at a faster speed. Means the response is very fast. GTOs, they can handle high power capability at slow speed. So IGBT is again medium capability and medium switching speed, just like this one. So medium level of switching speed and medium level of power rating. Further comparison, if we add more parameters over here, state of the technology, it is mature. IGCT is rapidly improving and it has become mature nowadays. Voltage ratings very high, 6.5 kilovolts, we keep on. So thyristor SCR is having a high voltage rating. BJTs, FETs, they cannot handle that much voltage rating. IGBT, GTOs, they can. Current ratings also similar. IGCT can handle large current rating similar to thyristor and GTOs. Now, switching frequency, we can say that BJT and FET, they cannot handle large voltage and current ratings, but they can handle large value of switching frequency. So 1 megahertz is the largest in this matrix of switches. So BJT over here, it looks like very difficult to use in power electronics. So drive circuit is also very difficult. So in that case, thyristors are normally used in power electronics, MOSFETs, GTOs, IGBTs and IGCTs. And IGCT is actually now replacing GTOs because they are fully controllable, just like GTO. You can turn on and turn off using the gate terminal. But the biggest advantage is that the gate drive circuit is very simple in IGCT. But in GTO, it is very difficult. So that's why IGCT has all the advantages of GTOs. And one additional advantage is a simple gate drive circuit. So that's why IGCTs are actually replacing GTOs. This is another way of showing that this is for ultra high power applications. Thyristors are used for high power. Again, thyristors are used. IGBTs are used for mid power or upper mid power and all this handling capabilities. For low power, MOSFETs and BJTs. BJTs are now, you can say, phasing out. So MOSFET family is actually being used for low power or ultra low power applications, just like in mobile phones, smartphones, and laptops. So here we are just showing the figure in 3 dimensions: voltage, current, and frequency. So MOSFETs over here, low current carrying capability, low voltage carrying capability, but largest frequency of operation. And as we move down the frequency of operation, we have IGBT. Even slower applications, we have GTOs, now IGCT. Even lower frequency of operation, we have thyristors, but they can cover large current carrying capabilities and voltage carrying capabilities. So based on this figure, you can decide, based on the applications, you can decide which device to be used as a switch in that particular application of power electronics. So ideal versus practical, once we have done with all the three categories of switches, we can now compare what is ideal and practical switch. So ideally, we want zero leakage in that switch. We want zero voltage forward voltage drop. So threshold voltage should be zero. Instantaneous switching. So no delays in switching. Zero thermal resistance. So the temperature should not have that effect. Infinite current capability. And it should support infinite voltage. And it must have a zero conduction loss, ideally. And zero switching loss between turning on and turning off. During that dynamics, the loss must be zero. Infinite temperature capability. And we saw that as the temperature increases, the false triggering on of the thyristor or SCR can happen. So if it has the capability of infinite temperature, so no matter how much temperature variations we see, so we cannot have a false triggering of the device. But this is an impossible dream. But still, we have come closer to these ideal requirements. We have come closer to the ideal requirements due to the advancements in switch technologies or semiconductor devices. Because MOSFET fabrication technology has developed so fast in the last couple of decades that most of these ideal requirements, we have come closer to these. Still not fully there, but still we can say that we have come closer to these ideal situations or ideal requirements. So, because we know that we are using these semiconductor devices as switches in power electronics because of the small power loss. And if we have a small power loss, we can have improvement in efficiency. So just by using semiconductor devices, we can increase the efficiency of the power electronic circuit. For ideal switch, when switch is open, no current flows in it, as we have said earlier in the last slide. When switch is closed, no voltage drop across it. We saw in ideal IV characteristics of all these devices. Since power is a product of voltage and current, no losses occurs in the switch because no current, no voltage, so no losses. So it means 100% efficiency. So these are the comparison we have already discussed. So now, after we know that, okay, what are the ideal requirements of a switch and what are the requirements or what are the practical actual variations of these parameters in switches. So how these variations of these practical switches occur compared to the ideal requirements. One is the power switch loss. Due to this power switch loss, the particular switch can vary all these parameters. So due to these, this practical switch can be different or it can be varying compared to this one.